So today I'm going to treat the following symplectic varieties. Of course, the original problem is as follows. X is a affine symplectic manifold embedded in the affine space as a complete intersection of homogeneous polynomial. So X is this one, like this. And I assume this is singular. Anyway, I would, in this case, if such holds, then X should be nilpotent variety of complex semisimple Lie algebra. This is the main result. So I'm going to generalize this situation a little bit, and I treat the following varieties. So now let's define the following class of symplectic varieties. So symplectic variety, say X omega is called conical if the following holds. The first, this is affine, so X is affine. So that means X is spectrum of some rings of finitely generated over C. And second, X has a good sister action. That means X has. That means explicitly this R is graded. If if X has a sister action, then R is graded by the weight of the sister action. And conversely, if R is graded, then X has a natural sister action. So that it is graded, but the good means that the grading is positive, non-negative, and R0 is C. This means that X is some sort of cone like this, and there is origin, and origin corresponds to the maximal ideal generated by the positive grading. This is corresponds to the origin. Yes, this is M, maybe better. So X looks like cone, and the sister action is something like this, contracting action. Yes, and third assumption is that this omega is also homogeneous. This is homogeneous with respect to this sister action. That means T star omega is TL omega for some integer. Yes, TT is T is C star. So if these conditions hold, we call it conical. So we are going to treat conical symplectic variety in today. So of course this is conical. This is of course this is conical symplectic variety. It is affine, of course, and it has a sister action. Sister action is a natural sister action, scalar action, and it homogeneous. Homogeneous is we from the first we assume that omega is homogeneous. So this is conical. So now let's start with such X. Yes. So now we can apply. X has a singularity, so we want to take a good resolution. So there is a theorem of Birka-Cassini, Heikon, McKernan. This is a recent big result of birational geometry. It says that there exist good partial resolutions, good partial resolution. That means first y has only q factorial terminal singularities, and pi is crepant. This means that ky is pi star kx. So this means pi is crepant. This is a big result of Birka-Cassini, Heikon, McKernan. If you start with arbitrary, if you take arbitrary resolution and start the minimal model program for such a situation, then finally you get some minimal model relative to x. And then the minimal model is nothing but this partial resolutions. So this is closely related with minimal model program. Okay. Now, but here you have a sister action because x is conical, so you have a good sister action. But this sister action extends to the sister action on x. So the sister action on x extends to sister action on y. This is not a trivial thing, but when x is symplectic, this partial resolution is semi-small. Very good. It satisfies very good condition. By using semi-smallness, you can prove that the sister action extends to sister action on y. I omit this part anyway. So this good partial resolution is sister equivariant in this way. Yeah. So this is symplectic. But how about this? So the next claim is y is also symplectic variety in a sense. So the situation is as follows.
Now x is a rational Lagrange tensor?
Yes. Now x is a conical symplectic variety. So symplectic varieties always rational Lagrange. Yes. So why is a symplectic variety? How to prove this? So you have x here, and you have this crepant partial resolution pi, and take a resolution of y. Y has some mild singularities, but take some resolutions. And here you have a regular part, and pi is crepant, so pi doesn't change the smooth part. So pi inverse of the regular part is isomorphic to regular part of x. And here, this is so smooth, of course, but this is contained in the regular part of y. Yes. And if you take the inverse image of this set, you get F, we call the composed map F, then F inverse X leg, and here. And here you have a symplectic form omega, and here you have symplectic form omega. Anyway, pull back here. And if you pull back this, here you have some holomorphic 2 form. It's not necessarily symplectic, but by the definition, X has symplectic variety. Then such a form extend to a holomorphic 2 form on Z. Yes. So this extends to some form here, and let us consider the inverse image of this regular locus of Y. Then we have the following situations. Yes, and by the definition of the symplectic variety, this extends to some holomorphic 2 form here. Then if you restrict it, then you get some symplectic, you get some holomorphic 2 form. And now, yes, and so this holomorphic 2 form defines always if you have a map from smooth, if you have a birational map from smooth varieties to smooth varieties, then the space of holomorphic 2 form is the same. So the omega is pushed forward to some symplectic some form on the regular part of Y. Yes. So, but omega Y is pulled back to omega. So, and this gives a symplectic structure on Y, and Y becomes symplectic varieties. And this is the outline of the proof. And this omega Y is naturally extends to this omega. So this is a symplectic varieties. Okay, so anyway, this is a symplectic variety. And now we have 2 forms here, omega Y and X omega. And it gives a Poisson structure and Poisson. And this pi becomes a Poisson map. This means that if you take fg from here, f and g are local function on x, then the fg pi star is nothing but pi star f pi star g. This is the meaning of the Poisson map. Yes. Okay. So now I will consider the Poisson deformation of both space and compare them. Before that, I prepare some definition of universal Poisson deformation. Poisson deformation. This is maybe formal universal deformation would be exact. But anyway, universal deformation. What is this? Now let Z be a Poisson varieties, any variety. Then a Poisson deformation of, say, big Z, this is small z, to be some the pair of the Z and the Poisson structure over some space S. It is a punctured scheme or punctured space is universal, or more precisely formal universal, if the following holds. If you have some for any Poisson deformation of this original one over Archinean local ring, A is local Archinean ring, and the residue field is C, and C algebra. C algebra like this. And if you are given such a Poisson deformation of Z over such a Archinean space, then there exists unique map from spec A to S, which sends this has a unique closed point, and this closed point should be sent to 0. 0 is the punctured point, and there exists a unique map phi, say, and this Z prime is the pullback of this family by this phi. So this such that Z prime is equivalent to Z times S spec A as a Poisson deformations. So always such map exists, then we call it universal.
But now S is just a formal scheme or
in our case, any scheme is possible. If S has such a property, then we call it universal Poisson deformation. Anyway, in the later, I construct such things for our X or our Y, but this S becomes algebraic variety in such a case. But anyway, in the definition, this S is some Poisson, some variety or some scheme, some space and something. This is not slightly different from usual universal one, because this is only considered a local Archinean Poisson deformation. But anyway, this is my definition of universal Poisson deformation. So now let's consider this. Then the theorem says that says there exists some sister equivariant commutative diagram of Poisson deformation of X and Y, universal Poisson deformation of X and Y, X and Y. The diagram is as follows. Here you have Poisson deformation of Y, universal Poisson one. This is a family of Poisson variety over CR, affine space, and here you have the family of Poisson varieties over CR, and this is the Poisson deformation of universal Poisson deformation of Y. So the central fiber is nothing but the original Y, and this is the universal Poisson deformation of Y in this sense. And here you have Poisson deformation of X. And these two universal deformation of X, Y and X are related with some map like this, and this is all commutative, and everything is a sister equivalent. So these are sister equivalent map, and these are all sister equivalent and commutative. And here you have a map phi, and this is the original pi. Yes, the original our pi. Yes. So, and this is, we call it the big pi. And this diagram satisfies the following properties, such that, and what is R? R is nothing but the Betti number of Y. Recall that yesterday I told you that the infinitesimal Poisson deformation is described by the second cohomology. If the such cohomology vanish, then Y is smooth. Yesterday I only treated single smooth varieties, but if the symplectic manifold satisfies such condition, then the infinitesimal Poisson deformation is described by this space. So in a case, so this is nothing but H2YC, and R is nothing but B2Y. And this is what is such that the following property holds. And first, phi is a finite Galois covering.
In this case, no obstruction to...
Yes. So Poisson deformation of Y is unobstructed, and the Poisson deformation of X is also unobstructed. And usually, if the deformation is unobstructed, you can construct the formal deformation step by step. But in this situation, by using the conical, X is conical, and everything is sister equivariant, so the formal universal family can be algebraized, and algebraization is realized on such affine space. This is the meaning, and the phi is a finite Galois covering, and second property is what is the fiber of such things. There exists the natural map for each point T. Here you have a natural map from yt to x phi t. Is always birational, and for all t, and it is and phi t is actually isomorphism for general t. Of course, if t is 0, this is nothing but the original Cripant partial resolution. It's not isomorphism, but on the general fiber, the pi becomes isomorphism. Yes, this is the meaning of the second statement, and the third statement is this is a local. This is a local trivial deformation. This is, we call this F. So F is locally trivial deformation as a usual flat deformation. What does it mean? This is a Poisson deformation. But if you forget the Poisson structure, it is just a flat deformation in the usual sense. And in the usual sense, F is a local trivial deformation of Y as a usual flat deformation. This means that if you take a point, any point here, take any point from Y, then there exists some U open neighborhood inside Y. This is a point in Y. So and there exists some open neighborhood of CR. This CR. So the open neighborhood of the origin, such that this is we call U, and such that U, we have a map from U to V. This is FU, and this can be trivialized in U times V. Here U is just U intersect with Y. Yes. So this means that this deformation, if you look at this deformation locally around P, this is just a product. This is a trivial deformation. This is the open neighborhood of Y itself, and this is a trivial deformation of U. Yes, this is a trivial deformation of U. This is the meaning of this. So, if Y has a singularities, then every fiber should have singularities, because by this assumption, if U has singularities, then every fiber over V has a singularities. So singularity doesn't change under this deformation. This is the meaning of the last statement. So this is the I want to apply this theorem, and I want to explain. If I have a time, I want to explain the statement. I want to explain the rough sketch of the proof of such a result. It's of course wrong, but I think I can say I can tell you the feeling of the rough sketch of the proof. So if I have a time, I will do it. But anyway, please admit it. Then now, what is then we have a following corollary. If this theorem holds, we have a following corollary. The first corollary is the following. X has a Cripant resolution if and only if X has a Poisson, has a smoothing by a Poisson deformation. What does it mean? So, for example, so the proof is like this. The first, let's consider, for example, if X has a Cripant resolution, then what happened? if y is clippant. It is if it is smooth. Yes. So if x has a clippant resolution, so if this is a clippant resolution, then we apply this to our theorem. We apply this theorem to this clippant resolution. Then we get the following commutative diagram. Here you have smooth, of course. But then, what is the general fiber? Of course, the central fiber is smooth. Then the general fiber is smooth. So then in this case, yt is smooth for general t, of course. But by using this assumption, this is isomorphic. So this implies that x phi t is smooth because this is isomorphic. And this implies that x has smoothing. Yes, this is this direction. And other direction. How about other direction? If a general fiber is smooth, what happens? So I want to prove that. Anyway, assume this x has a smoothing by Poisson deformation. Of course, x doesn't necessarily have a clippant resolution, but anyway, you can take q factorial terminal clippant partial resolution I explained, and take this. This is not a priori not smooth, but I want to prove that this is smooth. How to prove this? The general fiber is smooth, yes, but so the general fiber is smooth. So we take some. This is a surjective map. So we take some point phi t like this, and t is a very general point, and this is a surjective. So if we take t very general, that phi t is general. Phi t over phi t, it has a smooth fiber. So choose such t. Then by using this, we have a following map. But this is the isomorphism, and this is smooth by the assumption. So this is smooth. Yes. But the general fiber is smooth. But by using this assumption, if y has a singularities, then every fiber should have singularities because of the third properties. So y should be smooth. Yes, the general fiber yt is smooth, so the central fiber should be smooth by the property 3. So this, by property 3, y should be smooth. So this map, this gives a clippant resolution, not partial, clippant resolution. This is the corollary. And second,
so this is kind of generalization of a simultaneous resolution of rational double points.
Yes. This is a generalization of Brice-Cohn's picture. Brice-Cohn's studied such case for x is a rational double point, and Brice-Cohn slowly studied details in such a situation, and this is the higher dimensional generalization of Brice-Cohn slowly theorem. Yes. So the next corollary is the main part of this third lecture. The corollary 2 is the following. So let's return to the original situation of our main theorem. We have the following situation. This is complete intersection. the corollary is the following. Corollary. 2 this is the following. Assume that a conical symplectic variety X is of locally complete intersection. Then X always has a Cripant resolution. Pi. So this is the main claim in this third lecture. So if you apply this corollary to our original situation in the main result, then such X has original situation X is a complete intersection. Has only complete intersection. So X should have a Cripant resolution by this corollary. So this, okay, I will prove this by using this theorem. So now, how to prove this? Let's start with X and take some Q factorial terminalization. It is not necessarily smooth, but I want to prove that Y is smooth under the assumption that X is locally complete intersection. So how to prove this? So I want to prove this is smooth. Now, X is a locally complete intersection. Then its nearby fiber is also locally complete intersection. So X is locally complete intersection. Then the nearby fiber anyway, this is surjective, so we call it the phi t. Some nearby fiber is locally complete intersection. But this is here you have a map from yt to xt. But this is isomorphic. Yes. So this is isomorphism. So this is also locally complete intersection. But now Y has only terminal singularities. So Y has only terminal. This means that the singular locus has high codimension. Usually this codimension of Y singular point is not less than 3, usually. But in a symplectic case, the symplectic case, sing Y should have dimension, even dimension. So in our case, this is the even dimension. And so the codimension is also codimension of even. This is a Kaledin's result. Kaledin claims that if you have symplectic varieties, then a singular locus, the normalization of the singular locus is also a symplectic variety. So it has even dimensional. And Y is symplectic, so it has even dimension. So the codimension is also even. So the codimension is not less than 3, and this is even by Kaledin's result. So this means that the codimension is actually larger than 4. Yes. So the singularity has a big codimensions. But if the nearby fiber, this is a nearby fiber of Y, So yt is a deformation of y, and y satisfied this condition, then this yt also satisfies this assumption, this condition. So we have this. And yt is locally complete intersection. We obtain this. But here we have a following result due to Bobile proposition, due to Bobile. Let x, sorry, this x is maybe z is okay. Z is singular symplectic variety of locally complete intersection. Then the codimension z, a singular locus, codimension of the singular locus is satisfied this inequality. So the singular locus is big in some sense. But if we apply this proposition to this yt is locally complete intersection. If yt is singular, yes, if yt is singular and locally complete intersection, you can apply this. Then codimension should satisfy this, but it contradicts to this assumption. So by using this proposition, you have yt is smooth. So the general fiber, nearby fiber of y, general fiber is smooth. But the third property says that this is a locally trivial deformation of y. So if the general fiber is smooth, then the central fiber is also smooth. So this means that y is smooth. So this original Krippant partial resolution is actually a resolution. So we get the corollary 2. This is the proof. So I want to prove this proposition in the remaining.
You said the codimension is always even.
Always. So this means that this is 2. Yeah, this is actual result is this 2. But when Bobile proved this result, Karedin's result was not known. So this is 3. But actually this is 2. Yes. So anyway, it's a contradiction. Yes. Anyway, I proved this version. Yes. So the proof of this Bobile's proposition. How to prove this? So this is a local question. So codimension problem, and this is all local problem. So one can assume that Z is embedded in smooth variety as a complete intersection. Yes, this is smooth variety. And I will prove that. I prove that if the codimension of Z is not less than 3, then codimension, this thing Z is 3. It's enough. Yeah, okay. If the point is, if such, I want to prove that such things doesn't occur. Yeah. So if I suppose such things, then this is 3. So such things doesn't occur. So it's enough to prove this. Yes. So this is the strategy. So now assume this. The codimension is not less than 3. Okay. So how to do this? The idea is the following. The idea is the following. I consider this sheaf. This is the X sheaf. As you know, this has a support only on the singular locus. This is a sheaf of X. And I want to construct it free resolution. So here you have some map like this, S and X and normal bundle and the TX1. Yes?
I'm confused. So what do you mean by proof of Bobby's position? You said you proof of Bobby's position, right? Also you prove that, but already Bobby proved this one, right?
You will prove that Bobby's proposition.
I want to prove this result. So we don't know this now, yes? So, but we prove this. If we prove this, then Bobby's proof is okay. Bobby's proposition is okay. Is it okay? Because if this happens, so the point is that this doesn't occur. The point is that prove that this doesn't occur. Yeah. But if such things occur and this only happen, so this doesn't occur. Yeah. So I will prove this. So now, sorry, this is not X, Z. Yes. So Z. This is Z is a complete intersection. This is free. This is completely local. So this is free, and this is free. Of course, this is free OZ module, but it is not free because Z has singularities. So I have a trouble. But another sequence exists. Here you have the following things. Normal bundle. This is I. Is the defining ideal of Z. Yes. Then this is a conormal bundle, and this is a free and free, and this is the surjective. So the idea is to connect it. I want to produce isomorphism between theta Z and omega 1 because Z is symplectic. So it's roughly true because if Z is smooth, then the symplectic form identified with vector fields and one form. But Z has a singularity, so the problem happened. But now this is a this is a reflexive sheaf. So if we denote I the embedding of the regular part to Z, then this is nothing but I star theta Z leg. Yes, this is because this is reflexive. Then the reflexive sheaf is determined by the regular locus. So how about this? If this is I star omega Z leg, then theta Z leg and omega Z leg, this is a smooth and symplectic manifold, then this is identified. Then if this holds, then, and this is always true, So I want to prove this. So want to prove. Want to prove that I star z leg is z. If this holds, then this is same, and then this induces the identification of both sheaves, and then we get the resolution of TZ1. So anyway, we want to prove this, but I will prove it afterwards. Anyway, if this holds, then we get the identification, yes? And I will prove afterwards. Afterwards. Anyway, assuming this, then we have a we can connect these sequence, and then we have a following resolution. Theta is z, and this omega s1z, and I mod I all free. Yes, free. All are free. So the length is 3. This is length 0, 1, 2, 3. Length is 3. So the projective dimension of this sheaf as an OZ module is less than 3, because this is already pre-resolution, so projective dimension is less than 3, less or equal. But here you apply Auslander Buchsbaum. This is the famous result. The projective dimension is nothing. I take some point P. Take some point from singular locus of Z. This is closed point. And localize everything. At P. Then the Auslander Buchsbaum theory says that the projective dimension of this is depth of OZ P, the localized at D. Of course, P minus what is that? I forgot that. A depth of what? Depth of Tx1 Tz P. Yes. This is a Buchsbaum, Auslander Buchsbaum. But Z has only rational Gorenstein. So this is automatically Cohen-Macaulay. So if this is Cohen-Macaulay and this is a closed point, the depth is nothing but the dimension of Z, because P is a closed point, the usual point. So it is the dimension by the Cohen-Macaulay, and the depth Tz1P. Yes. So I have an estimate of the depth. What is the depth? So we have the depth is Tz1P is greater than dimension Z minus 3. Yes. By using this and this, and implies this. But on the other hand, depth is always bounded by the dimension of the support of this sheaf. Yes. But what is the support of this? This is nothing but the dimension of singular locus. Yes. Anyway, this is the local, but anyway, this support is, this doesn't vanish only at singular points, and at singular points it always appears. So this is dimension. So dimension dimension of a singular point is rather large. So this implies that the codimension of singular locus is less than 3. But original assumption is that codimension is bigger than 3. I have not yet used it because I will use this to prove this. So if this condition, we have this condition, then we get, and then we apply this argument. Anyway, the original assumption is this. So this and this implies that codimension Z is 3, and we proved the Mobile's result. So the remaining thing is this. So the remaining thing is just I proved this. I prove if this holds codimension, the thing is bigger than or equal to 3, then we prove this. Yes, this is the final step. So I want to prove this. This is all some sort of local cohomology. So we have a following exact sequence of local cohomology sheaf. We have a following local cohomology. We call, for simplicity, we put sigma to be the singular locus of Z. Yes, Z, yeah. So this, we have a natural map from O1Z to O1Z reg I star. And the kernel is nothing but H1 omega Z1. This is sheafification of the local cohomology exact sequence. This is the HZ, Z, not Z, sigma 1 omega Z1. We have the following. But I want to show this both Spanish. So I want to show this both Spanish. So claim this is both Spanish. Is 0. But we have a following exact sequence, as I explained. Yes? How to prove this claim? Take a local cohomology sequence. Then we have take this operator to this exact sequence. Then we get the following, not sigma, not Z. This is sigma, sorry. So this is sigma. Then this is sigma. Sorry, sigma, or sigma, yes. Then we have the following, HZ, this, not Z, sigma, yes, and sigma, 1, and finally you get H sigma 2 square. So I want to prove that this is 0. So this part, is important. In order to that, but everything vanish because these are all free. All free. Yes, this is free, and these are all free. So this assumption and Z is Cohen-Macaulay implies that this is 0 for I this imply this. This is a fact, well-known fact. So now we have following conditions and the Cohen-Macaulay, so this local cohomology vanish for such I. So this is the direct sum of such structure sheaf. So this is all 0. This is all 0. And this is all 0 because this 2. So this is 0. So this is 0. So we have this. Then we have here 0 and 0. And this is isomorphism. So we have this. And apply the argument and we get something like that. And this is Bobius proposition. Thank you very much.